All right, everyone. Welcome to chapter 1.4, where we begin to talk about functions. Now, you guys have all heard the word function before. Well, what is a function? A function is a special type of relation or correspondence between two variables. Oftentimes, it's a relationship between variables x and y, such that for every input, there is exactly one corresponding output. Now, I underline that because it's very, very, very important. That is our definition of a function. For every input, there is exactly one corresponding output. The domain of a function is the set of numbers or elements that represents all the input values for which the function is defined. These inputs are often labeled as the x values of the function and are referred to as the independent variable. The range of a function is the set of numbers or elements that represents all the output values of the function. These outputs are often labeled as the y values of the function and are referred to as the dependent variable. The value of y depends on what is plugged in for x. Now again, what makes a function a function? Each number in the domain can only be matched with one number in the range. Function notation is a way to name a function so that it can be easily referenced. Our inputs are often going to be x, and our outputs, as you will commonly see, can be f of x. Other function notations that you might see might be something like g of x or h of x, or once we get into some real life examples, we might talk about something like v of t, velocity, as a function of time. So here we have an equation. This is a nice quadratic equation, y equals 3x squared plus 7. Function notation simply means that instead of writing y, we are going to replace our y with f of x. F of x is equal to 3x squared plus 7 would be the function notation. And in any problem, if you're working on a singular problem, there should only be one function labeled f of x. Okay, we shouldn't label multiple equations as being f of x in the same problem. If you have multiple equations in the same problem, give them different names. Name one f of x, name another g of x, name another equation h of x. Just don't name them the same thing. All right, so let's do some examples. Determine whether or not the relation is a function. Again, relation just means a relationship between values. Well, in order for it to be a function, each value in the domain must be matched with a single element in the range. In this case, -2 matches with 5, -1 matches with 8, 0 matches with 6, 1 matches with 6, and 2 matches with 7. Is this a function? Yes. Each element in the domain is matched with a single element in the range. All right. Is this a function? We have our domain being the National League, our range for the National League being the Cubs, the Pirates, and the Dodgers. And then also in our domain, we have the American League, made up of the Yankees, the Twins, and the Orioles. Is this a function? The answer here, no. Each element in the domain is matched with 3 elements in the range. Again, by definition, for every input, there is exactly one output. Determine whether or not the relation is a function. All right, now we have a table of values. Well, this is saying if my input is 0, I get out -4. If my input is 1, I get out -2. If my input is 2, I get out 0. If my input is 1, I get out 2. And if my input is 0, I get out 4. Well, this is telling me that if I plug in 0, I'll get out -4, but also +4. If I plug in 1, I get out -2, but also +2. This means that this is not a function. We have 2 different outputs for the same input. All right, another table of values here. We have our inputs 0, 3, 9, 12, 15. The input 0 gives us an output of 3. Plugging in 3 gives us out 3. Plugging in 9 gives us out 3. Plugging in 12 gives us out 3. And plugging in 15 also gives us out 3. Is this one a function? Yes. All right. Even though the outputs are all exactly the same, each input has exactly one output. That is an example of a function. Now, testing for functions algebraically. To algebraically test whether or not whether or not a relation is a function, take the equation and solve for y in terms of x. If the result shows that each value of x gives out a single value of y, then you have a function. Okay? We want to see one value of y for every value of x. That means we'll end up with a single equation. Determine if the equation represents a function. Here we have x cubed plus y minus 3 is equal to 0. So again, what we want to do here is solve the equation for y in terms of x. That means isolate y. In order to isolate y here, we would have to add 3 to both sides of the equation and subtract x cubed from both sides of the equation. This gives me y equals 3 minus x cubed. Is this a function? Yes, right? For every input x, there will only be one corresponding y. I will never get out more than one y value. There's only one equation, y equals. Let's look at another one. Determine if the equation represents a function. Well, what would we have to do here algebraically to solve for y? We would first have to subtract x squared from both sides. That gives me y squared is equal to 8 minus x squared. To solve for y, we would have to take the square root of both sides of the equation. And hopefully you recall that whenever we take the square root of a variable, we must remember that there are both positive and negative roots that must be included. This gives me y is equal to plus or minus the square root of 8 minus x squared. Is this a function? No, this is not going to be a function because when I plug in a value of x, say 0, I'm going to get out two different y values. Notice that plugging in 0 for x gives us plus or minus root 8. This is not a function, right? The plus or minus implies two values of y for each x. And remember, in order to be a function, every input must have exactly one output. We can also test for functions graphically. To test whether or not a relation is a function, apply the vertical line test. If a vertical line is drawn at any location on the coordinate plane and results in more than one intersection point with the curve, the relation is not a function. Determine if the graphs represent a function. Right, here I have a graph, and notice I could draw a vertical line, a bunch of vertical lines. But no matter where I draw those vertical lines, it is only going to intersect the graph at one point. If it only intersects the graph at one point, it is a function. Every x value only has one corresponding y value. Every input only has one corresponding output. Okay, let's take a look at this graph. I draw a vertical line. I only have one intersection point there. That's okay. However, if I were to draw a vertical line here, now I have three intersection points. If you can draw a vertical line and it intersects with more than one point, it fails the vertical line test and your graph will not be a function. This is not a function, as one value of x can result in multiple values of y, multiple outputs for a single input. All right, and let's look at this one here. All right, let's draw some vertical lines. Does it ever intersect the graph at more than one point? No. No matter where I draw a vertical line, I'm only going to have one intersection point. Now, you might be a little concerned with this point right here, but Looking at the graph, I have an open circle, meaning that endpoint is not included. And here I have this closed circle, which means that this endpoint is included. So even though this vertical line goes through both of those, it's actually only intersecting the graph at a single point. Same thing over here. We have this filled in circle, which means that endpoint is included. Okay, and here we have this open circle, meaning the endpoint is not included. This vertical line only intersects at one point, right? Because of that, yes, this is a function. All right, evaluating functions. To evaluate a function, we simply replace each x with whatever quantity is given inside of the parentheses and simplify. Given the function f of x is equal to negative x squared plus 4x plus 1, find the following. Now, one thing I'd like to make note of here is that when evaluating functions, recognize that you are replacing the x's, okay? Here I have outlined the x's there in red for you. We have f of x is equal to negative parentheses x squared plus 4 parentheses x plus 1. And it can often be helpful to put parentheses around those x's so that you can recognize what you have to replace. So, what do we need to do to evaluate f of 1? Well, wherever we see an x, we plug in a 1. This means we have negative parentheses 1 squared plus 4 times parentheses 1 plus 1. All right, so we have 1 squared is 1 times a negative 1 is still negative, plus 4 times 1 is 4 plus another 1. That leaves us with negative 1 plus 4 plus 1. Notice that the negative 1 and the plus 1, those add to 0, and we are left with 4. F of 1 is equal to 4. When I plug in 1 for x, I get out 4 for y, and the ordered pair 1, 4 would be a point on that graph, the graph of this parabola. All right, what about evaluating f of negative 2? Well, again, whatever we see inside of the parentheses, in this case the negative 2, we are going to substitute that in for all of our x's. This becomes negative parentheses. And again, I strongly recommend you put your parentheses in. Negative 2 squared plus 4 parentheses negative 2 plus 1. Well, when I square negative 2, that becomes positive 4 times the negative in front. That's going to give me a negative 4 minus 8. So I have negative 4 minus 8 plus 1. Negative 4 minus 8 plus 1. Well, that gives me negative 11. F of negative 2 is equal to negative 11. When I plug in negative 2 for x, I get out negative 11 for y. And the ordered pair negative 2 comma negative 11 would be a point on the graph of that function. Now, let's take a look at this one. F of t. Well, the same concept applies. Whatever we see inside of the parentheses, that is what we are going to substitute in for x. And so what's inside of the parentheses here? We have a t. So what are we going to do? Substitute that in wherever we see an x. Negative parentheses t squared plus 4 parentheses t plus 1. Now in this case, not too much simplification that we can do. We end up with negative t squared plus 4t plus 1. See, we can even plug in letters. Here's one of my favorites. F of smiley face. Again, don't overcomplicate this. Whatever you see inside of the parentheses, that is what you are going to plug in for x. So, f of smiley face is equal to negative parentheses smiley face squared plus 4 parentheses smiley face plus 1. Now, again, none of those really simplify, and so we end up with negative smiley face squared plus 4 smiley face plus 1. All right, let's see if it can get a little bit more complicated here. What about f of x plus 2? Well, The same concept applies. Right here, I have an x plus 2 inside of my parentheses. That means I'm going to replace every single x in my function with an x plus 2. This gives me negative parentheses x plus 2 squared plus 4 parentheses x plus 2 plus 1. All right, so we can do out some algebra here. X plus 2 quantity squared. Remember, you'd have to FOIL that out, use the distributive property of multiplication. That gives me a negative 1 times the quantity x squared plus 4x plus 4 plus 4x plus 8 plus 1. When I distribute the 4 to the x plus 2, that gives me my 4x plus 8. All right, now I can distribute that negative 1 through. That would give me negative x squared minus 4x minus 4 plus 4x plus 8 plus 1. Combining like terms leaves us with our final answer, negative x squared plus 5. And that is how we evaluate functions. Okay, you will hear that a lot this year. I'll ask you to evaluate a function. Whatever is being plugged in for x, just replace every single x quantity in the function with that value. All right, there you have it, your introduction to functions.